Fun fact, I actually spent 7 years here in Raleigh. Both my kids are born here. So I hope you all can understand my southern accent. The Schneider Electric is the specialist in energy efficiency, and we bridge the supply and demand in some sort. And annually, we do about $3 billion business with utilities. And to date, we've built and designed and built about 150 microgrids around the world. We just started the work up in Faroe Islands in northern sea near Scotland with Dong Energy, the utility in Denmark, on a microgrid where a lot of wind, salmon farms, and flexible demand. So I wanted to share today some thoughts about utility microgrid. And I have really 3 key messages. Number 1, I believe strongly that microgrids are essential for the 21st energy-hungry world. I think microgrid will accelerate the electrification for people who don't have access to electricity. So we're talking the African continent, Southeast Asia, China, and so forth. But also commercial and industrial customers, electro-intensive customers like oil and gas, mining, or electro-sensitive customers like data centers, we'll see the business case more and more. We're reaching the inflection point of the technical, economical value of microgrid for these customers who want to be more competitive. And if electricity is a big factor in their cost, they will go with microgrid. The second point is that I believe that utilities can and should prosper with microgrids. Number 1 reason is making and delivering electricity is a serious business because electricity is a product that can kill. And because of that, safety is still our number 1 priority in our industry. And you cannot let anybody who has money start delivering electricity without controlling this. So that's the number 1 reason utilities should prosper. The number 2 reason is that actually most people who want to make their own electricity just want the benefit of the product. They don't want to be in the business of running a grid themselves. So there's another huge opportunity for utilities is to offer the service of building and operating microgrid. And the third message today is that this all works only if you build what I would call utility microgrid. And I will go into detail on what it means to design, build, and operate a utility microgrid. So in terms of essential microgrid, it's really the natural evolution of demand-side management. Energy efficiency, we heard this morning, very interesting panel, consumer engagement. Still a lot of work to convince customers to either modernize their appliances or change their behavior. Demand response, tremendous opportunity, moving from a fairly manual process where you call the customer so that tomorrow he can turn off his process to a real-time control. Like Schneider Electric in Europe, today we can control inside an industrial facility individual motors, individual processes, so that we can provide frequency regulation, fast reserve to the transmission operator in Europe. So demand response is really the main goal here. It's flexibility. Bring flexibility to the grid so that you don't have to jerk around these big power plants. And of course, we heard also this morning, DG is coming to fruition. CHP has been there for some time. With cost of gas here in the US particularly low, CHP will grow. We see that. We see a lot of people investing in these businesses. PV and storage are the next level with smart inverters. All this will evolve into microgrids in one fashion or the other. So let me give you 3 examples. One is, so these are US microgrids that Schneider designed and built. The first one is the University of Connecticut. It's a campus microgrid, which is always connected to the grid, but in case the grid goes into trouble, it can island and live on its own via fuel cells and PV and some batteries. The second example, it's a different type. It's a net zero community for the US Coast Guard in Puerto Rico. So this was a combination of very intense energy efficiency work with additional PV solar. So this is a boundary. This is a macrogrid in the sense that it's very limited, but it doesn't island and needs the grid to survive. And the third example here is in the city of Burbank, the local utility is now managing a distributed set of resources to compensate for the retirement of two coal power plants. So that's the term virtual power plant, when these resources are multiple, but in not such a limited boundary. So all these macrogrids are a good example. But again, I would say that to make the financial business case for the macrogrid, it has to be utility macrogrid. So what makes a macrogrid a utility macrogrid? It's a system of distributed energy resource that is always connected to the grid. But it can be disconnected, and when it's disconnected, it can live in an island mode for many days. So there's several kind of characteristics that needs to be achieved to qualify as a utility macrogrid. First, it needs to be seen from the grid as a controllable load. So it really is to bring flexibility. Second, it needs to contain some renewable, because if it's all about burning diesel and gas, you don't get the credit for saving the planet. So a utility macrogrid needs to have some renewable content. And then how does it work? It can either be behind a single point of connection, or it could be a virtual network of distributed resources. But today, I'm really going to talk about the scenario where the macrogrid is connected to the grid via one point of connection. So with that design, you have the following benefit. First, flexibility for both energy and capacity. So now the load, the ultimate tool for demand response, if you will, is this utility macrogrid. It means that the utility can control what's going on. The qualifies renewable because it has itself a content of true renewable, wind, solar, biomass. It improves resiliency of the power system in two ways. First, the load it serves can survive a major outage on the grid. That's typically what we talk about when we improve reliability. We keep the light on for the load. But in terms of resiliency, it can help the grid come back to power, into a black start mode or into some kind of restoration process by accelerating zones that are more critical than others and contributing to re-energizing the grid. Again, very importantly, this has to be coordinated by the utility. And in terms of the overall cost, I'll show you why it at the end of the day, it reduced the overall cost of energy for much more than just the owner of the macrogrid, for the society. So in short, macrogrid brings flexibility, reliability, and stability. It's a way to shield the grid from the variability of renewable and other things that may happen through a controllable connection point. So when you want to finance these macrogrids, because that's another barrier of this new market, is how do you finance such a capital investment? Really, you build a business case for all stakeholders: the utility, the owner of the macrogrid, the ratepayer who shares the grid but doesn't benefit directly from the macrogrid, and the society. The utility will have a cost because now in a utility macrogrid, the utility must be involved in siting, in engineering, in testing, and must upgrade its system to operate the distribution grid. But the huge benefit is that it doesn't have to use transmission and distribution assets to serve that load. That load is now self-served, avoid generation. And of course, the cost of infrastructure to integrate renewable is also avoided because the macrogrid takes care of that. In terms of the owner won't do it if he doesn't see the business case. And the business case would be, in terms of benefit, lower cost of fuel. So he has decided that for him, it's cheaper to buy gas and make electricity than to buy electricity. And he has also put a value on being independent from the utility, either because of security, reliability, marketing reason. Maybe they want to have an image of a green company and so forth. But because he also contributes to the grid, in that design, he should get credit for renewable and get credit for helping the overall reliability of the grid. So that's kind of the business case here. The ratepayer should benefit from the avoided infrastructure cost that the utility doesn't have to make because the microgrid is being built for them. And when you think about it, the utility now has the same amount of people can really focus more on the customers who don't have microgrid. So the guys who have microgrid take care of themselves. Utility can provide a better service, better power quality to those who don't. So the ratepayer should see it as a benefit in the sense of the utility serving them better because they don't have to serve the guy who owns the microgrid anymore. And society, of course, less pollution, better environment in general, and then economic development. The whole idea is that this creates jobs. This is a new market. This is a new growth opportunity for the local territory. And then if the public buildings use utility microgrid to produce energy, then we should pay less tax to support their budget. So this is actually very active today. I'm sure most of you are aware of what's going on in the Northeast in particular. So utilities have done that reasoning. The smart utility, we call them smart utility. They've went to regulators and say, hey, wait a minute, there's a cost-benefit analysis here. I should be able to justify a rate case or regulated investment. And it's also substitute grid extension and generation buildup. Or some more progressive utilities have already started businesses to extend their ESCO services into building microgrid. We are currently discussing several of them in partnering with them to deploy and operate microgrid. There's also some utilities who invest in technology, so they just put their money in companies that they see will benefit from that growth. And of course, public-private partnership, in particular in cities. So here's some quote that I took from some of the recent case in Central Hudson Gas in Connecticut. The governor put $30 million there. In New York City, the post-Sandy report said that utilities should incorporate microgrid expansion into their planning. Minnesota wrote a report that says that they would encourage utility to expand the scope of their planning to consider the benefit of microgrids. So I think we reach an inflection point, not only from a technical and economical point of view, but we are about to reach that point with regulators, state commission in particular, who are now more and more convinced that this is a benefit to all of us. Again, I'm talking very specifically of utility microgrid. How do you design a microgrid that can benefit the grid and society in general? You have 4 key criteria. One is islanded, meaning make sure it works when it's islanded from the grid. There's no point of building a microgrid that will depend, on the utility to survive. That defeats the purpose. There's supply-demand, which is very tricky in a microgrid because it's a much confined area, and you got to be a lot smarter in bridging supply and demand, controlling both at the same time. The connected mode, very important because that's part of the value of the utility microgrid, is to contribute back to the grid. So that has to be very controlled and specified by grid code, if you will, just like we have on wind farm now. We have a second generation of grid code for wind farm where the power is no longer just take in, it has to be controlled. And then last, the configuration plug and play. As part of the big difference between the microgrid and a traditional grid is that things are moving a lot more. The configuration is very dynamic. The loads come up and down. The generation, same thing. It's not a stable infrastructure. It's meant to be very dynamic. So the way you design it has to take that into account. In the islanded, so in terms of the island, one thing I wanted to highlight is availability criteria. So again, it's where utilities should see the opportunity, because if you're running on the microgrid for several days, you have to think about maintenance, spare parts, and so forth. You become a utility operator. Stability criteria, if you have to run water pump, you're in a storm, you have flood, well, these motors requires a lot of inrush current, so you have to have design that support that. You don't have inertia in the grid, so any power system engineer would tell you it won't work. It does work, but you got to design it for it. In terms of supply demand, it's really the key thing here is that you have to have a real-time forecast. You have to be very close to understanding what's your load and what's your supply. One angle here is energy efficiency, because a lot of somebody said it this morning, it's no point in building this fancy microgrid if you have very inefficient buildings and so forth. So part of the supply demand is to reduce the demand first by having a very efficient facility. In terms of connected, tie-line control, both for frequency and voltage, ramp rate. You don't want a microgrid that provide too much power, or so there's all these characteristics well known when you talk about connecting wind farms and so forth. They should apply to these utility microgrid. And also, one source of revenue, if the owner wants it, he can over-design his generation so that he can trade power back to the grid for market purpose. So that would be part of the design consideration as well. When it's connected to the grid, also the microgrid can be requested by the utility to support what's called maintenance mode. When the utility typically has to isolate an area of the grid, they do switching. Well, instead of just switching, feeders or even putting people in the dark, they could ask the microgrid to contribute to the switching plan and energize some part of the distribution grid because they're trying to fix another part of the grid. So really look at it as an integral part of the utility grid. And in terms of the plug-and-play configuration, what's important here is two things. The microgrid needs real-time measurement and automation. It's really running in second by second, and the operator, the way they look at things, is quite different from the utility. They have to be a lot more alert, but also more able to anticipate issues. So again, that's another opportunity for utilities here because operating a microgrid will become more and more complex, and I don't see people, facility managers and so forth, being willing to do that themselves. This is the architecture of a Schneider microgrid. In the bottom, you have the real-time acquisition and control. You notice we talked about flexibility assets. We don't talk about loads anymore. So the whole range of what you can use to manage the demand versus generation. In the real-time operation and control, we have a very tight connection to weather. So Schneider Electric provides a worldwide weather service for utilities that is bringing the weather data into if you will, a process that translates weather data into forecast for load and supply. This is a graphical picture of the utility microgrid. You recognize the point of connection here and the CHP providing heat and power. The potential for a DC bus, because a lot of sources are DC and a lot of loads are DC. And then we have a microgrid management system that can communicate via secure communication to people who can see what's going on. So that's one aspect here is the segregation of loads. So contrary to a utility who considers mostly loads equal to each other, here it's very important to isolate critical loads from loads that want to participate in demand response from loads that just would be a regular load and would suffer from outage if needed. And then lastly, a view of operating a utility microgrid. So you look at it at three functions. One is predictive control. So the first dashboard here shows you how your load and your generation evolve, knowing that generation has a renewable content, so it's not like a stable flat curve. And then you have the real-time control inside the microgrid, which is sort of a mini automatic generation control to maintain frequency and voltage. And then you have supervisory control, which is where the utility tells you what to do from their distribution management system, and you automatically respond to their signal. So in conclusion, if you look at, and all this, by the way, these are systems that are accessed via the cloud. You don't need to install all these computer systems on site. In 2050, I believe a distribution grid will become, I think Gary said this morning, a grid of grids, a network of microgrids. And the question is, do we let prosumers, people who have money and want to put fancy microgrid in their facility, take over and create havoc, or do utilities become smart utilities and proactively promote this concept of utility microgrid? And what it means is, first, they need to see the revenue coming from the service they provide. Second, they need to educate regulators and put together a rate case for designing a benefit cost analysis that justify this utility microgrid, and of course be proactive in how you specify and how you can connect your microgrid so that they can truly isolate the power variability from the grid while taking advantage of the avoided infrastructure and the incremental renewable. So that's what I wanted to share today, and I will take some questions now if you have. Thank you.
Thank you very much, Thierry. What a great concept here. We do have time for a question or two. What policy would be the #1 policy change to create a grid of microgrids instead of creating the havoc that you alluded to? If you could have one policy, what would help most?
I think today it's the connection standards, IEEE 1547, which hide behind it a policy issue, which is back to the danger of providing power back into the grid if the grid is de-energized. So if a line is down and somebody is connected to the grid and re-energize that line, it is actually a danger. So all this has driven this technical standard.
Right.
We represent a policy that says, instead of trying to figure out how we can connect microgrid to the grid, we're simply going to not allow them to connect. So that's the #1 policy, is to really transform this connection standards to enable the business of microgrid.
Perfect. Thank you very much.
Thank you.
I really appreciate it. Thank you.
Thank you.